In Extradosed bridge, the bridge decks are pre-stressing internally as a normal pre-stressed girder bridge or cable-stayed bridge. In addition to this, cables are also used as externally pre-stressed cables. This two pre-stressing process act simultaneously and make the bridge deck stiffer and stronger that allows a long span and can carry a huge amount of loads.
Tower height of Extradosed bridge is generally lower than the tower height of cable-stayed bridge. For this lower tower height, cables form a flatter angle with the deck of the bridge. Reduced cable inclination leads to an increase in the axial load in the deck and a decrease in vertical component of force at the cable anchorages. Thus, one of the important functions of the Extradosed cables is to pre-stress the deck. Extradosed bridge usually rely their load on only 20 to 50 to cable, and remaining portion is covered by the girder as it is more stiff than the stiffening girder in a cable-stayed bridge.
Two. Modeling and analysis.
Through Extradosed-Study. Ten different prototype models as well as simple models of the bridge has been created and analyzed through Extradosed-Study.
2.1 Steps of bridge modeling. Important steps associated with modeling of Extradosed bridge will describe briefly. At first, the required nodes are arranged for developing the model. 3 types of distance related with node to node, that is distance in x, y, z direction. As ours is 2D model, so x and y direction distances are considered. Distances in x and y direction for a node are provided with respect to first node where distances are 0, 0. There are 86 nodes used for forming a prototype model. Whole span, cables, pier are denoted as beam. All the beams are created by draw line in between the nodes using beam courser, and created 132 beams are generating the model.
Among these beams 48 are cables and remaining beams are girder, tower and pier. After that, sectional properties for different parts are defined. Rectangular and circular section used here. Whole structure can divide it in 4 main parts, that is girder, cables, pier and tower. Pier and cable section are circular section whereas girder and tower are rectangular one. For modeling, roller supports are used at 2 ends of bridge. Because only gravitational loads are considered and lateral loads are ignored for the analysis. Again, the third Carnifoli bridge is designed as continuous bridge 3.
For follow this condition, roller supports are used at the ends. Fixed support is used below the pier. The rest portion below the pile cap is ignored. Loads and cables are also defined in next step. Self-weight is considered as main load for modeling. Lane load is considered as uniformly distributed load. For defining the load, 2 load cases is formed.
Then self-weight is assigned by selecting whole section and UDL is assigned only on girder. External cables take the 20-50 loads of total load 4. In the actual third Carnifuli Bridge 7F36 cables are used 3. In this modeling equivalent cable diameter is used. The cables are defined as member tension only. Consider that cables will take tensile force only. After defining it will assign in selected beam. Simple models are also created by following these steps.
(2.2) Analysis of the model.
The prototype models generated based on actual span and girder section of third Carnifuli Bridge. 10 different prototype models as well as simple models are developed for study on different parameter like tower height, cable angle, axial force and stress of girder and cable. Variation of deflection of girder and cable are also observed from these models. In all models only variable is their tower height. Analysis of model helps to meet the purpose of this research.
(3) Resultant discussions.
This paper represents the results found from the analysis done by the software. Table 1 and Table 2 summarize the results or prototype and simple models.
The variation of different parameter with respect to change in tower height as well as angle of cable is observed by plotted various curves for prototype models. The graph Fig 2, shown below, is angle of cable versus tower height graph. It demonstrates the variation of angle of cable with the variation of tower height of prototype models. As the tower height increases, the angle of the cable with girder also increases. Maximum cable angle 37.57 degree found for the maximum tower height 40 m. The curve is a linear curve.
Change in angle of cable influence the compressive force of girder as well as tensile force of cable. So the variation of axial force of girder and cables with the variation of angle of cable is observed by plotting the following graph Fig 3. Max compressive force curve indicate that, as the angle of cable increases, compressive force of girder decreases. Maximum compressive force of girder 65,128.90 K. Takes place for an angle of 21.03 degree tower height 20 m. After this maximum point with an increase in cable angle, girder axial force is decreases. Maximum compressive force curve found for different tower height is a linear curve.
Again, maximum tensile force curve of cables also indicates same behaviors as maximum compressive force curve. As the cable angle increases, the cable tensile force decreases. The maximum tensile force of cable 16,528.36 kN also occurs for the same cable angle 21.03 degree. Stresses of girder and cables are also varies as like as axial force of girder and cables. The variation of deflection of girder and cable with change in tower height for prototype models are shown as following graph Fig 4. It represents that deflection of girder decreases with the increase of tower height, whereas deflection of cables increases gradually with the increase of tower height.